Welcome to APEC. It's October 22nd, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Ted Pittman will discuss the impulse driver. Phil Bouchard will describe finite theory. Mike Melia is going to talk about his inertial propulsion experiments. And Mark Sokol and Professor Kieth Earle will be presenting on their ongoing work with the Alzofon dynamic nuclear orientation experiment. We'll be finishing off the event with an open discussion and ad hoc presentations by conference attendees. So a couple of quick reminders: you can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type those questions into chat, and we'll go through them after each presenter finishes. Okay, so let me introduce you to our first guest. Ted Pittman's impulse driver achieves a net linear force by combining gravitational and inertial forces in a complex cycloid motion of oscillating mass. The upward half of the pulse isn't canceled during the downward half cycle. Thus, precession reversal is avoided and a net upward linear force is achieved. Ted is going to describe his invention and discuss recordings showing acceleration data during testing where the impulse driver successfully rose to the upper mechanical limit of the test stand. So let's welcome Ted to today's event, and I'm going to hand things over to him to get started.
Okay, hello everybody. I don't have access to my computer files right now because I have a Chrome laptop, and unfortunately Zoom does not update, or Java does not update Chrome computers anymore, and I needed Java to put my Chrome online. So I'll be just using this video and the audio in my presentation. Not really much to report since the last input that we gave, which is now on YouTube. I've moved a lot of my equipment out of my garage. The weather's getting ready to get cold, and put a lot of that stuff in storage because of where we're at with the project. You may recall, for those of you that heard me speak before, that the next step in my project was to make a quad version of what I had patented, the impulse driver. And all along, since the beginning of the project, way back, the idea was to make an engine, inertial propulsion engine. And when I patented one cylinder of that proposed engine, that was enough to prove that the idea worked. That is, that it gave a net lift. And now we're at the point where the 4 cylinders, which are actually there are 3 duplicates of the first one, identical duplicates. We're at the point now where we're looking to combine them, some sort of skeletal structure, kind of like the tree branches holding the 4 together and so on. And I have to say thanks to Mark, because the way I was doing it was literally taking 4 of the, let's say, patented devices and connecting them in a very crude way. But that required 2 electric motors for each cylinder, with a total of 8 electric motors. And Mark suggested, well, let's do it with just 2 motors. So I looked at him like, this guy thinks he's that smart. And it turns out he is, because he suggested you put 2 motors in the center, one pointing up with a shaft. Motors, these are electric stepper motors that drive the unit. One pointing upward, one pointing downward. The one pointing upward goes through actually a gear and then pulley belts to drive the 4 cylinders. They just need rotation. And it's a duplicate down on the bottom. So now we're moving towards, we already have the electric motors, we have the 4 cylinders. It's just a matter of designing the pulley system with the belts, which is not a big deal. I did it before. And so that's the latest update. Once we mechanically connect the 4 together, then of course we'll be running it. And the whole idea of this, since it should be obvious that 4 of something doesn't necessarily do anything different than 1 of something. But with the one cylinder, there was always the lateral motion involved, which was not helpful to what I was trying to accomplish. And it also left the doubt that perhaps everything that I was seeing on my test stand was related to stiction, which is friction between the impulse driver in the center of the test stand and the Teflon rollers on the aluminum guide rods on the side. And even way back, it had been suggested that a machine like mine could just be kind of climbing like a ladder left and right with stiction, friction coming up. The most recent test we did at Falcon Space put that aside because they had a different counterweight system set up. And again, you can see this on YouTube. And it was very simple in the sense that there was a fulcrum attached to the side of my elaborate test stand. And then a short distance away, there was a connection to the impulse driver, which was down in the chamber. And then, of course, the lever arm all the way out. I think it was about 24, 36 inches out. And we had 1 pound of weight out there. We had done a quick calculation on what was needed. And we could see that everything was balanced. And also, Mark had a very high-speed camera running because for the first time, we wanted to see the actual orientation of the disc as it's pivoting, and at the same time be able to see the top of the impulse driver to show that it's moving upward. And that's significant because with all the gyration going on from the gyroscope, the engine looks like it's bouncing around. And when we're not in a counterweight test like the one I'm describing now, that's all it does is bounce around on a load cell scale. The point is there's more force coming upward than downward. It's measured by accelerometer as well as a stress gain.
Ted, I'm terribly sorry to interrupt, sir, but I do have your YouTube channel up. I know that you're not able to do that with your laptop. Would you like me to do a share screen and we could play some of your videos?
We could do that. I could synchronize with that. Let me finish with a couple of minutes more.
Absolutely, sir. My apologies.
Okay. So we'll show you what the setup was. And the good news is, and I was as surprised, probably more surprised than anybody in the room, the impulse driver rose faster than it had ever risen in my tests. And we attribute that to a couple of things. Not only the friction between the wheels and the angle irons on the side, which have always been there, but in my test setup, there were 2 pulleys over to a counterweight, and the pulleys themselves apparently were contributing friction within the whole test. And I hadn't accounted for that. It's a pretty silly mistake, but I hadn't accounted for that. I thought the fact that there was a counterweight equal to the engine's weight on one side and the engine itself on the other side, that maintained an equilibrium. But the engine was pulling against the friction of the pulley wheels as well as any other friction that was in there. You'll see in just a minute how quickly the device rose. It amazed me. I don't know about everybody else in the room, but there was silence there for about 60 seconds. But anyway, going on, I just want to say something about 3D printing. For me, it was a nightmare. I had an Ender 3D printer, and I spent more than a year trying to master that thing. And I didn't, I failed. My grandson came in at one point and said, "That looks like nice abstract art." I wanted to smack him and send him out of the garage, but he's a comedian anyway. So moving ahead, as far as what's the direction to go, the last 2 things on my goal list, which is also out on YouTube, and you can see it in a minute. The last 2 things was to make the 4-cylinder engine, which we're about to complete, and also to make a neural network to control the system. And When you see my earlier videos, I'll talk about a pivot encoder, so I won't talk about it now. It turns out the pivot encoders collected a lot of data, which is useful, but the data showed that the disk is in chaotic motion unless it's at resonance. And resonance is very hard to achieve and maintain because of the freedom of movement of the gyroscope. It's on an axle and it moves freely. It's not driven directly by anything. Anyway, let me move on a little bit. So the solution for that is to do a neural network, which I can use more than the data from more than 100 tests that I have recorded, digital data about this one device. I can use that as inputs to a neural network. Neural networks take positive input, which is what you want, and neural networks also take negative input, which is what you don't want. And the network works some kind of magic with the software so that it learns how to recognize when some other inputs that you give it will be useful or not useful, positive or negative on the output of the neural network. I did some work with that years ago, but that's irrelevant right now. That's about it right now. The best strategy for running my machine without the pivot encoder and without the neural network was just pulsing the system at the right time. And we did that. We found that just by rote, just testing over and over, and we were able to maintain the lifting force over long periods of time. I had I had several videos that I could have shown you, but that'll be for next time. Right now, Tim, if you're there, I would like to show the previous videos from the last show.
Yes,
Tim?
absolutely, absolutely. Sorry about that.
And
I was muted. So let me do this. Let me queue up. Okay, I've got your channel. So I'm going to do share screen, and there we go.
Remember, I can't make selections. I'm just on my phone.
Yeah. So let me see. We've got counterweight test August 24th. You want to start with that one, or?
What's the other two?
There's ultra high speed video of the impulse driver, and then there's a impulse driver test. There's a gamma drive update about 6 months ago, and then an impulse driver.
No. Let's do the counterweight test and then the high speed video.
Okay,
please.
So let me start with that. So we're kind of going in reverse order. So the counterweight test, and here I'm going to, oops.
There's no audio. There's no audio with this. The video speaks for itself.
Yeah, in fact, I'm going to turn the audio up.
Speaking. So here's the test setup, which was at Falcon Labs, Falcon Space. You see it with a new counterweights up at the top of the test stand, not that big concrete block that had been there for years, and more standard equipment. The second shot here zooms in on the connection point between the lever arm and the wires that are running down to the impulse driver. And then you see the pivot, and out here, the guys are still adding the fish weights. Actually, there were 8 2-ounce weights. And then we'll jump right into the test. It's going to be quick. Lifting. You notice I'm pointing down at the bottom. There was so much gyration going on that I didn't even notice how far up it had gone. For those of you that have gone to my YouTube site, you'll remember that the engine had never lifted that quickly. Now I think we'll take a close look at, not that, a close look at the high-speed video. Okay, what we were looking for here, and I recognized it. I'm not sure that anyone else in the room at the time did. We were not at perfect resonance, and I'll explain that in a second, but the gyro disc pivots outward when it can. By that, I mean its orientation. If when you look at the bottom of it, the flat, shiny part that's coming around right about now. Okay, you can see right there, it cannot pivot as it passed. So every 90 degrees, there's an opportunity for the disc to pivot, or mechanically, it's restricted from pivoting. And basically, that means its most powerful momentum can be achieved from one side of the vertical axis, 180 degrees around to the other side. However, when it's only 90 degrees around the basic circle at the bottom, then it's the structure of the gyroscope is such that it's not able to pivot. It basically slides down the spindle, okay? The top view of this is explained in one of the videos out on YouTube, but we were able to verify the motion that was going on here. I don't recall how many frames per second it was. I think Mark can tell us, because the camera that was being used can run 10,000 frames per second. The little circuit board that's on there is the pivot encoder, which has an RF transmitter, and the sensor tells how far the gyroscope has pivoted. There's similar sensors up at the top for the position of the orienting motor up the top, and for the position of the rotating motor that's under the bottom of what you see here. When everything is synchronized well, then you get the lifting force, and it, I don't know if it can be obvious in this video, but up at the top, you can have a lot of vibration with this system without any lift, no apparent lift that can be seen. And once it gets into resonance, it's obvious that it is giving lifting impulses in a vertical direction. So that's the quick story of what we're doing. The only thing to do after the four-cylinder, the four-cylinder engine will eliminate the problem of friction, because we don't have to do it the same way we've been doing previous tests. And of course, it counterbalances lateral forces. So all of the excuses of why it works other than my theory will be gone, I believe. It's been a long time of trying to prove that the system works. In the future, I don't know if it's distant future or near future, I hope to have very small models of this invention, and of course, approach the proper people in aerospace for its use. And that's my story for now.
Okay. And let me see. Perfect. Perfect. Ted, thank you so much. Thank you so much. So everyone, let's give Mr. Ted Pittman an enormous applause, an enormous applause. Thank you so much, Ted. I can't thank you enough. And it was wonderful. I had so many comments in chat about the excellent video as well. The high-speed camera looked just absolutely smooth.
Thank you, Tim.
Yeah, absolutely. Does anybody have questions about this?
How you doing, Ross?
And I'll allow participants to unmute themselves. Yeah, so if anybody has questions, there's Ross has a question. Go for it, sir. Oh, Ross, you're muted, my friend.
Not really a question. It's more just, wow, that high-speed video really finally puts this in perspective and lets you see exactly what's going on. Because previously, you know, when you're looking at that, it's so much going on because you got those universal joints and you have the gyroscope that's kind of, you know, like you said, cut in half. and so you're kind of, your mind is so can't wrap yourself around it. But now that you've got it in that high-speed video, it's like, okay, now I can really see what's going on. So you started off with the idea of a gyroscope, and then you like you said, you cut it in half so that you could have another pivot point right there on that. And so I could see mechanically how, now I could see where that would be the only way to do that, to pivot a gyroscope like that, is if you were to cut it in half like you did there. I don't think a lot of people realize like how fast that's actually moving. Like that high speed video, it really showed it slowly spinning around, but
Right.
I mean, I can imagine it must be spinning tremendously fast.
Well, it was only 300 RPM
That's
on the
still
lower
fast.
part, and 130 RPM on the upper part. And it turns out that if I spin the spindle, the upper part, if I spin it too fast, gyroscopic forces themselves prevent the pivoting. We all know if a gyroscope is spinning fast and you hold it in your hand, it's hard for you to move it. So there is a limit to the ratio of speeds between the upper motor and the lower motor before I get into gyroscopic forces that work against me.
Wow. I mean, that idea with the universal joints, how you have running down the middle, that shaft at that, you have all this multiple universal joints that allow that shaft to do such a thing, to go down.
Yeah, at the bottom, Ross, the shaft, the spindle, it's just loosely in the bearing down at the bottom. There's no firm connection. That's why it's able to go around and spin around at the same time. It's just sitting through a bearing.
It reminds me like an 18-wheeler truck, how you have the engine up front and then you have the axle on the back, and you have like a drive shaft going down towards to spin the back wheels, and they have to have multiple angles, multiple universal joints, because sometimes the truck will go over hills and things, so the drive shaft has to be able to be flexible and stuff like that. So mechanically, it's a very genius how you came up with that idea to do that.
Yeah.
Well, thank you. It wasn't something where I just sat around and stared at the ceiling and said, aha. These things, a lot of it came from just experimenting, and all of a sudden it would do something unexpected, and then I investigated and moved ahead. One last thing, Tim. Over the years, I found many different resources for mathematics, physics, and other things that I had not been educated on formally. And I have the websites and books recorded as far as the authors or the websites for many different resources. So if any of you would like to see a list of those helpful pieces of material, just send me an email at tedpittman09@yahoo.com.
Okay, wonderful. And actually, I am just, let me see. I will paste that into chat as well. There we go. And you said it was 09?
Yes, tedpittman09@yahoo.com.
Oh, at yahoo.com. Okay, I have
Yes.
a Gmail account for you.
Well,
okay.
I have two accounts.
Yeah, there we go. There's the Yahoo account, tedpittman09@yahoo.com. Thank you, sir. So let me go to Harold, and then after that, and Harold, before I should mention to everybody, Jeremy Reese just called me in a panic. He said his children tore apart his computer. He is unable to present today. He's putting pieces back together. So that does put us considerably ahead of schedule. Let me apologize for any inconvenience that we're causing. So after Harold's question and Mark's question, we'll go to Mr. Bouchard, who will be presenting on finite theory. Harold, let me go to you, sir.
Can't hear you, Harold.
You're still muted, sir. Oh, Harold, you're muted.
Excellent video. It's
hey, how you doing, Earle?
Oh, doing fine. Good to see you still doing it.
Same
Question
here.
for you. How fast was it spinning, the RPM? And the second question is, uh, can you have, more than one gyroscope in the same shaft that they wrote that when one is not producing thrust, the other one is producing thrust? I mean, have you considered that idea? I mean, have you something like that?
Okay, in the test that you saw in the video, the speed on the lower motor was 300 RPM, and the speed on the upper motor was 130 RPMs.
Okay.
And years ago, we tried using, for instance, two gyroscopes on opposite sides, but it turns out that it made the unit much wider, just so the gyroscopes wouldn't hit each other and whatnot. And we didn't pursue that very much after that. The principle would still work. Plus, there's geometries that you really have to think about, that they're not so obvious just looking at the system. The further you move the bottom of the spindle away from the center of the central vertical axis, the more you change that tilt angle and the more you change the pivot forces. So we had found that 20 degrees was some kind of optimum. You don't want to be less than that because you're not accomplishing anything. But to have basically two spindles, you would have two units, okay? And it's kind of what we're getting ready to do, because all four units on the quad system are going to be driven by one motor. It just comes up through the center of the whole thing, and then with gears in the center and the pulleys, it'll be turning the motors.
Oh, I see. Would that be similar to working like having a 4-cylinder motor in which
Yes.
each? Oh, okay. Well, that sounds like a good idea. That's a good approach. That probably make the thrust very continuous, more like closer to the straight line.
Yeah, exactly. Exactly.
Wow. We're looking forward to see you next time you have it completed and have a demo again, because that would be an interesting one to see. Hey.
Oh, yes. Oh, yes. We'll do it before the end of the year. That's for sure.
Oh, excellent. Well, looking forward to it. Thank you very much. You're doing good work. Keep on making progress.
Thank you. Thank you. How have you been doing?
I'm doing fine. I'm doing some experiment, making progress, and waiting for them to give me my patent. I mean, I'm keeping my finger crossed. So far, everything looks good at this time, and it might end up being a pioneer patent, because as far as I know, I mean, the theory I worked out, it turned out to be good. The only person I know that came close that have guessed it is the German Hoyer, Detlef Hoyer, when he came up with the multidimensional, which I was working, I mean, I was getting hinted, that's what it was, multidimensional thrust. And so far, I see multidimensional thrust every time I turn on the machine. So I'm making more measurement accurate, to making sure to compare and confirm the mathematical equation that drive the unit. But that is excellent. But I gave up, on inertial propulsion a long time ago. But after seeing you and Sinclair and Ross, working that, and Mark Melia producing those effects, I feel, there must be something, because NASA killed it a long time ago. And the reason why the patent office does not give any patent on inertial propulsion devices has to do with the Mark Melia 2002, the NASA wrote a paper. And he sent me one, and the paper basically said, gyroscopic anti-gravity is dead, doesn't work. Later on, I read that the patent office, using NASA work, decided, you know what, no more patent on inertial propulsion because it's dead. And that's why you had a hard time getting it. I did, I never got any of mine, so it's one of those things, I produce some bad machines, some good machines, but anyway, but now it seems to me like you're working, making progress, you're challenging the criteria. So if you are very successful in the end, in which you can prove all these things, then, you might open up a new avenue, a new road to follow. It's like the Ross machine, didn't work when he made the test, but the thrust that his machine is producing is 90 degrees off. That's why he's not producing, the straight. But if you examine again, go 90 and look it up, because gyroscope, the changing angular momentum, the input of the force that causes the changing angular momentum, the output force is 90 degrees off from the input. That's what is happening in Ross. So yours have it, in which you are doing something different. I mean, it had to be mathematically interesting at that point, and so it seems what you're doing is very different, so that there's a new door opening right there. That's what I see so far, and I hope you get a lot more success with that. So, and I appreciate and I thank you. I look forward to see the four-cylinder working.
Wonderful.
Okay.
Well,
Thank you.
And Harold, thank you for the information on Mark Millis in the patent office. Also, that's something I wasn't aware of, and so thank you for sharing that. So let me go to, let me see, Falcon Labs, which I think is Mr. Sokol. It is.
Yes. Yeah, I think Keith, you have to shut that off. So this is something we were working on with Ted when he was here. We called it the gravity diode. It's basically making 4 of those devices. This is the top-down view, X configuration. And we'll be using belts to transfer the power from the center motors out to all 4 of them. And the reason why we called it the gravity diode, as Ted can say, is because the symbol that he wanted to use to describe the gyro in the center was actually the shape of a diode. And when you put 4 of them together, it's sort of like a full bridge rectifier. And hopefully with this design, we'll be able to put the entire thing on a pendulum, or just hang it straight from a string without having too much wobble, because one would counteract the other. That's at least the idea. And hopefully we'll be able to see some straight weight loss without any possibility of stiction being involved, because if it's in free space hanging, can't be any stiction. Also, Michael Perrone, who drove in from Massachusetts over here, he has a great idea in inertial propulsion that we wanted to share, and he started writing on the board as well. I'm gonna grab
I don't need any further. So if you think of, if anyone remembers, a couple months ago, NASA produced a paper regarding a particle accelerator. Okay. So NASA produced a paper a couple months ago regarding a particle accelerator, where you have the particles moving faster on one end and slower on the other end. And because of the change in relativistic mass, you get a propulsive force, but it was very small and took lots of gigawatts of power. So if you want a similar thing in a home lab, in principle, do we have the screen?
Yeah, that's it.
Okay. In principle, you could just use 2 bike wheels and get a similar effect. So you have a stationary rod, you have a rotating structure attached to 2 bike wheels. The bike wheels are stationary on the rod, and they have a large angular momentum at some distance. So they have a slightly increased relativistic mass relative to the base. And in principle, the downward acceleration around the outside of this should produce more force than the upward acceleration here because of the relativistic mass. Now, you're not using a particle accelerator, so the speeds are much lower. So your relativistic, the change in that, the difference in those 2 accelerations is tiny, but you have a lot more mass than a particle accelerator. You have many more, you have like 10 to the 23 more particles than in a particle accelerator, although the speeds are much lower. So you have a small exponent, but a big constant in front of the exponent. So in principle, you might be able to see something measurable with that apparatus. So I would be interested if someone could build this. I have no time for it at the moment, but go ahead and try it. Yeah.
Are the large wheels locked in place that they always remain against?
Yeah, so you may want to add some sort of gear at the bottom to make sure that they are, but I mean, just a piece of sandpaper. And if these are bike wheels, they'll be rubber, so the friction coefficient will be very high. So it's likely that you'll have stiction at the base. And then if you apply the torque to the two wheels at their centers, then they'll just spin anyway. So
Yeah. So Michael, you're directly describing Ted's device, right? Or
I think that this could be a closely related effect, considering the relativistic behavior at some angular distance. But this would be much more simple. I mean, you wouldn't need machine learning or anything. It would be a steady state force. You'd have lower vibrations, so you'd have a bigger signal. And it's just overall simpler. There's a lot fewer, like there's some precession you have to take into account, but and then also this apparatus could accidentally climb up this with stiction due to the precession. So this whole block would have to be like weighed as a whole thing. You don't want to weigh this separately from the rod that it's on.
Hey,
and
Mark,
Yep.
could you, is it possible for you to move the camera real close and just scan across the whiteboard once for everybody to see what's there?
wonderful.
So you got your two bike wheels and a stationary rod. You have some 3D printed whatever to hook up to the two bike wheels, and then you spin that 3D printed whatever around the rod, and the two bike wheels will just by their contact with the rod in the center, they'll spin naturally on their own. And then you'll have a slight amount of relativistic mass at the outside. The acceleration should be ever so slightly larger.
Okay. Yeah, I just want to try and keep things focused on Ted's idea. So that's
Okay.
yeah. No, I think it's absolutely wonderful. Thank you so much. I just I don't want to leave Ted behind. This is his Q&A session. So
Well, sorry.
And this is the 4-bridge rectifier gravity diode contraption that we're planning on building next.
So and this is something. So Ted, are you going back to Falcon Space? Or are you going to be back at the lab with Mark?
Yes, occasionally, yes.
Okay, well there you go.
Yeah, Ted has been a regular occupant of the lab in the lab house. He's been coming over here quite often. Moved all his stuff into the storage locker next door. So we've been working on this pretty regularly, actually.
Yeah.
You know, I was gonna say, Mark, your lab is turning into a tourist destination. You should start selling something. I was like, wait a minute, you get the t-shirts. There you go. But you know what you need?
We're running out of t-shirts, by the way.
Yeah, you need a coffee stand too. You need a coffee stand. You have a little barista over in the corner. You know,
I need somewhere to put my RBI machine too. So if you want me to bring it down up there,
I thought you were parking that halfway in the wall. I thought that was your parking spot. It was halfway in the wall.
Bring it down here. We got a forklift and we can move it around and set up a pendulum system for it.
yeah, it's close to 300 pounds. You probably would need a forklift. But for real,
Jim Crowley's giving us the chairs.
I would bring it up there, and y'all can have it and do what you want. You know, I'm kind
Cheers,
of,
guys. I like the idea of a bistro kind of in your garage there. It would be perfect.
Oh, there is a coffee room though, and there's also a vapor deposition room over here, and Faraday cage and a whole bunch of other stuff.
Well, you could put the barista right next to the vapor dep machine, right? So
We'll vapor deposit some
yeah.
coffee.
Well, no, I think it's exciting to have Ted back in, and I think that's one of the wonderful things about the lab that you've got set up, right? Is that you were able to have people like Ted come in and do experiments there, and you've got tooling and machines set up, and then you guys are able to work together and share ideas, and I think everyone benefits. So it's really exciting.
Yeah, to me, it's just an amazing and wonderful facility for the kind of work that we want to do. All my life, I haven't seen anything like that as far as the availability of resources to do to promote these types of ideas. So, thank you, Mark.
Now, Ted, what does Mark need that he doesn't have? This is your chance. This is your opportunity. What's he missing?
I can't think. Well, I guess if I try hard enough, I can think of something that could be added to the lab. But it's more than enough equipment for the things that I've even imagined, and I mean that seriously. He's a very serious guy doing very serious work in a very serious way. And I can't say enough good things about him, especially from the standpoint of what we're trying to accomplish.
Well, you know, and sorry, I feel a little guilty because as moderator, I'm talking more than I'm probably supposed to. But, you know, seeing that 300 RPM high speed test, Ted, your work is also impeccable. I mean, it was so smooth seeing those transitions. And that was high speed, right? And I didn't see rattle or shake or anything like that. It seemed like it was
Mark,
very smooth.
What was the speed that day, Mark? I don't think you had the camera cranked all the way up, did you?
Oh, no, that camera can go up to 1.4 million frames per second. We had it turned way down to like 5,000 frames per second or something like that with higher resolution. Yeah, we had to keep, I started it at 10,000, but that was too slow. So we had to crank it to slow it down a bit so that you could actually see the movement happening.
Now, if I can ask in that video, there was a circuit board. What was the circuit board, and why did the circuit board have to be attached inside of the moving parts? Because I'm sure that made it more complicated to construct.
Well, that's the pivot encoder. And I took a lot of measurements on everything that I could during this project. And there was no way to know the exact angle of the gyroscope because of all the motion that's going on, unless you're right along with it. And so I made an encoder wheel, kind of like a clock with spokes to the center. And then I made a sensor that would send a beam out and get the reflection back. So as the gyroscope pivoted, we would get a reflection and lack of reflection and so on. So we would get signals which were going to the data stream. And all of my data was synchronized, even the videos. I had a little light that I would flash in the video stream that would also send a signal to the data recording. So everything was recorded. And that's why I was telling you about the neural network work that I'm going to do. There were everything that could be measured was measured as far as movements on this machine. I just haven't had the time to analyze it all because my goal has always been to see it lift. And if it lifts, that's the final answer to what I'm trying to do.
Okay, wonderful. Well, let me see. Any more questions for Mr. Ted Pittman? And again, that is Alt-Y on Windows or Option-Y on Mac to raise your hand. Okay, well, so let me do this then. Let me put this back in gallery view. Ted, thank you so much. Thank you so much.
Thank you.
Let me thank not only yourself, but everyone in the audience as well for your flexibility today. We normally have a little bit of chaos. Today we have a little bit more than usual. So Ted, thank you again, sir. Thank you very much.
Okay.